Good morning, class. This is the lecture for Tuesday, September 15th. And we'll start by going over the homework problem. And I'm going to start by going through homework 1, problem 2. So you were supposed to find an exercise website and look up the calories per hour for going up a treadmill at different percentage grades or inclines for a 70 kilogram person walking at 5 kilometers per hour. And you should have just been able to plug all that in at some website. On the website I found, okay, so the incline (0, 2%, 4%, 6, 8, 10, 12, 14, and calories per hour that I looked up: 286, 327, 365, 438, 501, and 564, 627, and 690. And then you were supposed to convert this to watts. And hopefully that was no problem for everyone. Basically, you just use the conversion factor that you can find in the notes. And so 333 watts. And I'll just do this in the interest of time, and to 802. So of course, the higher the incline, the more power, the more fuel power you must consume. And then basically, you were supposed to calculate mg v vertical, which is the power in lifting that you're getting out of this. Basically, it's you can think of it as the useful work performed by the person and lifting themselves. Now you can get philosophical about that and think in terms of, well, useful work would be something like the person carrying something, up a hill or something like that. But here we're just going to sort of count useful work as the person being able to carry themselves up the hill. And the only wrinkle here is, all right, we went over that energy is work times distance. So power, oops, I'm sorry. Energy is force times distance. So power is force times velocity. That's if force is constant. In this case, the force is constant because it's the force of gravity you're working against. And the only wrinkle here is that has to be replaced with a dot product. Because of course, if you're just going flat, if the grade is 0%, you're not doing any lifting work because your height hasn't changed. So now you can either think of it as a dot product. I think it either think about it that this is the velocity in the direction of the force, which in this case is vertical. So you have to do a little geometry where, okay, as the person's walking up the incline at 5 kilometers per second, Okay, and you have to do a little geometry there, and I'm going to post a homework solution. I'm not going to walk through all this geometry together, but basically that results in a certain piece of vertical, depending on the grade. And you do have to take into account that the grade, as I said in the when I handed it out, that the grade means like 10% means going 15 feet up for every 15 feet. Like a grade of 10% is going up 10 feet for every 100 feet of horizontal travel. So there's a little bit of mixed geometry there. And I'll leave that to you to go over with the homework solution that I'll post after the video today. I'm just checking my focus here, which looks okay. Hopefully it'll stay good. All right, so if you work that out, you basically come up with mgb vertical as 0, 1938, and 132. So you were asked to plot one versus the other. And so this is basically, and I'll use the W for the fuel power. I want you to get used to thinking about fuel consumption as a power. Basically, you know, energy per unit time. That's your calorie consumption on the x-axis. And you were supposed to put mg be vertical on the y-axis. And if you do that, you find that as you plot for the different grades here, so you start out at 333 and 0. Now what that means is basically you know, of course, if you're just going horizontal on the treadmill, you're consuming calories. And that's equal to, according to the website that I found, 333 watts that you're consuming just to maintain that speed going horizontally. And you can sort of compare this particular result with, as we went over in the notes, that you know, if a person is consuming 2,000 food calories a day, if you do the conversions, that works out to 97 joules per second, or 97 watts. And so this tells you that, and that 97 watts is sort of your average consumption, or maybe baseline consumption. And then when you're actually, you know, running horizontally, your consumption goes up to this much. And the difference is sort of the excess that you have to do in order to maintain that running. But anyway, if you plot it, what you find is that this goes up, you know, to around to 38 at that incline, and then for some reason it goes slower after that. So basically it has kind of two straight lines to it, and I mean, I wasn't going to put up the projector today because I can do everything on the board. So you know, the first thing, and I asked you to sort of like, you know, say something useful. So basically out here at, so this would be 0, 2, 4, 6, 8, 10, 12, 14, and at 14 that's 802 watts. And that corresponds to 132. And so the point of the exercise, I mean, one of the things I wanted you to sort of comment was that, well, of course, this number is smaller than that number, because if it were bigger, and I hope none of you turned in an assignment where you plotted that this number was bigger than that number, because that would mean that somehow, miraculously, energy was appearing out of nowhere. You know, the the flow of energy in this situation is, okay, the person ate something at some point and had stored chemical energy from that in their body, uh, and uh, and then they were able to utilize that energy to perform this exercise, and the burn rate in watts has to be greater than the delivery of useful power. Um, and so of course 802 is bigger than 132. You could make some comments about the differential efficiency here. This slope goes up at 42%. That's kind of interesting to me. Basically, it means that on a differential basis, as I incline from 0 to 4%, okay, my sort of differential efficiency is 42%, meaning of that extra energy I had to consume in my body, 42% of it, of that difference, wound up as useful work. That's pretty impressive, really, and it sort of tells you that our bodies have kind of been designed to walk up hills. that the treating us as a machine, we're pretty good at, meaning, basically this is 38, and that's 365. Did I do that right? I'm sorry. Yeah, no, it said 333. Yeah, 330. I'm sorry, that's not 365. I'm using the calories per hour. At 4%, that's 424. Okay. And so as I went from a 0% grade to a 4% grade, my food consumption had to go up from 333, which is what I needed to stay horizontal at that speed, up to 424. And the result of the sort of useful work of me going up the hill was 38 watts. So 38 over 424 minus 333, if you do that, works out to 40.42. Which means that our bodies, in terms of the excess fuel required in order to walk up a slow grade, we're very efficient. I mean, 42% of that excess power or energy wound up in the useful work of carrying us up the hill. Now after that, it slows down. This is 25% differential efficiency. So basically what it means is that at this speed, okay, which, I sort of made up 5 kilometers per hour. That's kind of a fast walk or a slow jog, kind of, however you need to look at it. But up to a 4% grade, we're very efficient. And then after that, it takes a lot more fuel energy to result in useful output. Okay, now, so we're talking about fuel consumption and useful work output and efficiency and things like that. So basically, the question is, like going from here to here. Well, first of all, let's start here. This 333 watts. Where did that energy go? Because, okay, we burn fuel inside of our bodies, and it had to go somewhere. And okay, the answer is not that it wound up in more kinetic energy because my speed is constant. It didn't wind up and work against gravity because my height is constant. So it all has to wind up as heat. So when we're doing this exercise on a horizontal thing, all this power is having to wind up as heat somewhere. Now, later when we talk about vehicles like cars, and we sort of already have talked about that a little bit. If you're driving a car down the freeway at 70 miles an hour at a constant velocity, you're consuming a lot of fuel, right? So your fuel power is very high, and your speed's not changing, so it's not changing kinetic energy. And where is it? Okay, it's winding up as heat. And I've told you before in a previous lecture that for the vehicle, where it's winding up as heat is primarily at those speeds and heating the air as you move through the air in your vehicle. And I guess you might try to say analogously here that some of this 330 watts is winding up heating the air as you move through it, except for the fact that you're on a treadmill, and so you're not actually moving through the air. So that can't be any of the answer. Which incidentally, I've often wondered if you could calculate how much harder it is to run outside where you're actually having to pass through the air versus up a treadmill where you're not actually moving through the air. And I mean, the answer is pretty much that, well, I mean, remember power and wind, okay, and sort of it works backwards too. The power that you have to expend going through the air goes as V cubed. So the difference between this at 5 kilometers per hour versus the car going 75 or 70 miles per hour is enormous. And so even if you were jogging and outside, the heating component of the air would be almost non-existent at these speeds. And you know, but it often has made me think that, okay, should it actually be easier to run on a treadmill than outside because I'm not having to go through the air? And you know, pretty much the answer I always come to when I do either one is that it's easier to run outside. But I think that's just psychological because I'm not bored. But anyway, getting back to here, that 333 watts wound up as heat somewhere. Now the other place, and as we, like when we discuss vehicles, we'll discuss the fact that as you're driving the car, you are heating the tires, and in fact the road as well. So heat winds up there. Okay, and in this case, you know, some of the heat could be winding up as, you know, heating basically your shoes kind of, and maybe the treadmill to a certain extent, because, you know, you're undergoing some fractional friction every time you step, and so you're applying forces down there, and some of it could be heating. Now, there, you know, you can kind of make an estimate because, you know, I've done this where after, you know, jogging or running on a treadmill, so you're inside and stuff, and, you know, feeling whether your shoes actually got hot, and I never really been able to tell that they got hot. So, you know, I think the answer is, you know, maybe a little bit. But, you know, getting back to our light bulb, you know, kind of example, you know, 100-watt light bulb, how hot it is, you know, I would say that, you know, the heating of this 333 watts, the amount that ended up heating your shoes and or the treadmill through the you know, that process, I mean, I'd be surprised if it was 10 watts. Okay, so hardly any of it. So where's it going? Well, it's heating our bodies. Well, almost all of that power is being dumped in heat in our bodies. And now, and you know, you kind of maybe realize this, that you kind of get hot when you exercise. Now, you know, we talked about the efficiency of us as a machine and things like that. Now, the efficiency of us, you know, going horizontally is very kind of minimal if you think about it, because, you know, we're, you know, when we do this, we're mostly, you know, generating heat within our bodies to keep this process going, a huge amount of heat, really. Now, where is that heat going? Okay, so as we're running or doing any sort of exercise, we're generating a tremendous amount of heat in our body, and where is it going? Well, okay, so you could start to think of the answer as that, well, okay, we are actually getting hotter, okay, and I think actually when you exercise, your body temperature does go up a little bit, but very minimal. Our bodies are very good at maintaining that constant temperature, and especially on a Kelvin scale, that would be minuscule. So, the heat is not staying in our bodies. If it were staying in our bodies, our temperature would be zooming up as we exercise, and it doesn't. And so, you know, if I were in an in-person class at this point, I would be asking people, well, where's the heat going? And someone might answer that, well, okay, there's only a few ways it can exit our bodies if you think about it. I mean, one is through our breath, that every time we expel a breath, we're exiting heat from our bodies, okay, and a fair component of that is that, but the majority of that is through sweat. And as we exercise, we sweat. It is our primary heat shedding mechanism, and so the mechanism there is that our bodies generate water on the surface of our skin that evaporates. Okay, it takes energy to evaporate, and so that heat in our bodies, that excess heat in our bodies, essentially is being used to boil the water on our surface and evaporate it. And so that energy is conveyed off in water vapor, and that's how we shed this excess heat that we're developing. Which actually it was an interesting thing. One of the first few years I taught this course, there was someone in the class that knew this, which apparently is true, that the fact that we don't have fur means we can do this through our whole body. I mean, you think of a dog, right? The dog's equivalent mechanism is to pant, and so he's sort of evaporating water from his mouth as a heat shedding mechanism. Whereas we can just sort of develop sweat across our whole body, and it can be so we have a very efficient heat shedding mechanism. So actually our prehistoric ancestors used this ability because this ability to shed heat like that gives us a tremendous advantage in stamina, because we can maintain a level of exercise of several hundred watts for a long time, all day basically, and not overheat our bodies. Whereas our prey, as a prehistoric animal, we would hunt down animals. They had fur, and so they did not have this shedding mechanism. And so basically, what I've been told, and what I've kind of looked up, is that a hunting mechanism of early man was to, as a band, sort of just chase a herd of animals all day long until finally they just, through exhaustion, just fell over, and then we would move in. It's the ability to sweat, meaning that we don't have fur, which I guess means that we had to develop clothing. That's a whole evolutionary mechanism that you now understand through treating our bodies as a machine having energy processes. Okay, so let me move on. Now I'm going to discuss homework, the problem 1, in the context of the lecture here. All right, so focus. Yes. So what we've been covering are, and let's put it this way. Let's say sources of energy. And I'm going to qualify it on the Earth, meaning on our planet. Okay, on our planet we have access to these energies, and there's stored chemicals, meaning primarily oil, coal, and natural gas. There's stored nuclear energy. If you refer to I just do it from memory. So these are our primary stored energy, and then there's solar energy, meaning the sun is incident upon the Earth, and we can utilize that power. And that can be direct solar, like solar cells. That can be things like wind, which is essentially a result of solar energy, hydroelectric, or bioenergy, which is basically plants and stuff. And these are what we have available to us on the Earth. Now, there is, okay, part of the reason I gave the homework problem is that there is another sort of more planetary source of energy, and that's tidal power. By the way, stored nuclear energy, this includes geothermal. Because geothermal energy comes from the heat within our Earth, which is a result of radioactive decay of heavy elements. And I'm not going to belabor that here in this lecture, but you can read that in the notes. And it works out to 44 terawatts total. And I have some discussion there about how that 44 terawatts is spread across the entire globe. And so, maybe we can access, I don't know, maybe 1/100th of that or something like that. And so, there might be, 440 gigawatts. And remember, that's of heat accessible. 1/100th. Okay, so, these are the things we have. Okay, now tidal power. That results from the interplay between the Earth and the Moon, and everyone kind of knows, how tides work. Basically, as the Earth rotates, the pull of the Moon causes a bulge in the ocean surface, and so you have this sort of bulge of water that's rotating around the Earth. And you can sort of calculate what that is, and I go through it in the book or in the notes, and it's sort of I don't know, it's sort of a rough calculation. It's basically to understand that you have to understand the interplay between the rotation. You have to understand where the energy comes from, and where the energy comes from is from the mechanical system of Earth and Moon shedding kinetic energy. And in fact, you may think that comes from the Moon somehow slowing down. In fact, the Moon is speeding up and going further and further away from us. But the Earth's rotation is slowing down. And that's the primary where the energy is coming from, is the Earth's rotation. And you can kind of work out that this is, about 1 terawatt. All right, and the way to think about that is similar to geothermal. Okay, it's a lot of energy, 44 terawatts. By the way, a terawatt is 10 to the 12th watts. But it's very hard to access. And so again, here, there might be 100 gigawatts at 1/100th, meaning if we're able to, accessing tidal energy is very difficult. There are no commercial generation systems that I'm aware of, and it basically relies upon you having some sort of bay or estuary where a lot of water goes in and out every day. And so right now, while there is, you can see it on your chart in the front, there's geothermal power being utilized. There's no tidal power right now. Now one of the reasons for doing problem 2, or problem 1 of the homework, where that started was, okay, now let's start to think kind of crazy where we could get energy. And as mentioned here, tidal power really kind of comes from the kinetic energy in Earth's rotation, and basically, that tidal power is sort of a derivation of the fact that is slowly getting slower, and so that kinetic energy is being shedded. But if you so if you take the Earth, somehow draw its axis, and it's going like that, and it's rotating. Okay, so So I was going to calculate the kinetic energy in the Earth's rotation, and so the first year I taught it, I was like, well, that's a good homework problem, and so that's where that pain came from. But I think it's a good exercise because not only is it kind of partially relevant to what's going on here, but it's a good mathematical exercise to train you how to do this problem of of performing this, where you're summing all the kinetic energy. And hopefully most of you realize that, okay, you can divide the Earth up into a bunch of cans. Chalk. Where, okay, now here, okay, the relevant dimension is the distance from the origin, so you want to use cylindrical coordinates. In cylindrical coordinates, the sort of distance dimension is the distance from the axis. And so if you had a can like this, you can imagine an empty soup can spinning. That basically, if this was dr, then first of all, the velocity is just like the notes, 2 pi r over t. T is 24 hours in the case of the Earth. And you have to calculate the differential mass. Okay, so the differential mass is the density rho, which is why I didn't use rho up here for cylindrical coordinates. That's the density of the Earth, and that's times the differential volume of that, which is basically just like in the notes for it's 2 pi r dr. That's this area, so to speak, times h of r. And you work out a formula for h of r in terms of r, and so it becomes this integral from 0 to r of rho 2 pi r dr h of r times 2 pi r over t squared. And I'm not going to go through the whole derivation here. Again, I'm going to post the solution. But basically, if I can find it here. There we go. Okay, it works out to 4/5 m pi squared r squared over t squared. If you got the right answer, okay, you'll realize that this is the kinetic energy of the sort of flat flywheel. From the notes. So the kinetic energy of a spherical flywheel is 4/5 of that, which kind of makes sense if you think about it, because an equivalent cylinder would include these spaces here at higher at high velocity that are not included in the sphere. So it kind of makes sense that the sphere should have a lower total kinetic energy. All right. So if you plug in for the Earth, all right, for the Earth, m is 6 times 10 to the 24. Oops. R, the radius of the Earth, is 6,370,000 meters, and T, right, is 24 hours. So that works out to 86,400 seconds. But this is then equal to 2.6 to 29 joules for the Earth. Now that wasn't part of the assignment. I wasn't asking you to calculate the kinetic energy stored in the Earth's rotation, but I'm just sort of plugging in numbers. And so the Earth represents it's like a big flywheel essentially, and so it represents a tremendous amount of energy storage. And if you could tap this over 1 billion years, 1 billion years, meaning if you somehow could tap the Earth, convert that kinetic energy into other energy that we might want, like electricity or something like that, and do it over 1 billion years, meaning whatever technology we came up with to perform that conversion, it would be such that the Earth starts slowing down, where in 1 billion years it slows to zero, which I don't actually know if that's far enough out for the whole process that, to be okay. But then it works out to 8.1 terawatts. Now here, if we could really do this and access all of that 8.1 terawatts, it's not like the geothermal or the tidal where we can get kind of 1/100th of it, if we work really hard. If we had some sort of mechanism, we could actually, make a lot of use of that, because that is a lot of power. Of course, there's no way of doing that that anyone's thought of. I mean, because it's like, well, how would you? I mean, you could sort of imagine that, if you were God, you have sort of you put a magnet, on the Earth, or well, actually, you have to go the other way. So you have north and south, and then you'll learn that you generate electricity by having a large coil. Okay, so you have some large coil, and so you treat the Earth like a dynamo. Actually, not a dynamo, a rotating magnet generator. And so as it's rotating, okay, every time north and south goes past this coil, you would generate a lot of current, and so it'd be like a generator. But of course, no one knows how to do that, and certainly not on your chart for 2050 are you going to envision us placing large magnets on the surface of the Earth and coils in space. But I mean, in principle, far in the future, I mean, who knows? I mean, maybe you could put large magnets on the surface of the Earth and big coils out in space, and somehow utilize this energy that's there. And I'm just saying this sort of preface, that, well, when we talk about sources of energy, it's what's practical. What can we use really, and it's pretty easy to. Well, it's not easy, but it's straightforward to dig up oil and refine it and put it in your gas tank and power your car with it. Whereas you can see when you get more exotic, okay, then you have to start putting coils in space. So this is kind of it. Now, I preface this by saying, sources of energy on the Earth. Well, sources there, we can look beyond. Maybe, like I'll just say in the solar system. So, I mean, here's the sun, here's the Earth, sort of orbiting around the sun. And way out here, I mean, okay, so here's Saturn, all right, and there's Titan, which has huge, methane, etc. So I mean, again, I mean, this is like the coils around the Earth and stuff like that. In the far future. Okay, people think about, hundreds of years from now, and in hundreds of years, we will require enormous amounts of energy, um, because if for no other reason, to correct the effects of climate change, which will take energy, basically huge amounts of energy to remove the CO2 from the atmosphere that we've placed there. And you know, I mean, you think about this system, all right, all right. If I somehow was able to load little craft, with methane on Titan, I built some sort of station, and I loaded up a tanker with refrigerated methane, which would be easy since it's so cold out there. And I launched this thing. Okay, I'm kind of going downhill, right? And it's, I have to get off of Titan. I have to get out of the Saturn gravitational influence. But I'm sure you could sort of work out the orbital mechanics that if you could do all this. Now, I haven't looked this up. I don't know. But maybe, 100, 200 years in the future, there's a way where you can launch this tanker off of Titan, so that the energy it took to launch it out of this system toward the Earth and then put it, in orbit there, and then bring it down to here, that maybe the energy that you would gain from the methane, so this thing's going like that, the energy you would gain from the methane you transported is greater than, hopefully much greater than, the energy it took to do this. And that's called energy return over energy invested. And so basically, right now, this is basically mining in the solar system instead of Earth. And right now, mining on the Earth, and when we go over oil wells, you'll see that most oil wells, conventional oil wells, I mean, you're under pressure, you just plunk down a hole, if you do it in the right place, it comes shooting out all on its own. So the energy return is almost infinite, because, you almost have to do nothing for that oil to get up there. Now you have to consider, and so there's sort of two ways of thinking about energy return. And one way is this, which is that once you've set up the operation, okay, am I getting that energy back? But the other way is that you have to think about all the energy it took to build this system to begin with, and sort of people argue about how that should be included in this whole thing here, and you can think about that. So this isn't the homework problem. This isn't going to happen by the year 2050, and so it's not in your final project. But I'm just illustrating that if you think far into the future, okay, way past 100 years or 200 years, that everyone kind of envisions, for example, that the nuclear fusion will be worked out by then, or we'll work out techniques. I mean, on a simpler basis, we'll work out techniques for disposing of nuclear waste safely, or something like that. I mean, the way technology and engineering in the energy field could go 200 years from now is that, well, no, I mean, we're going to start mining the solar system, because we've worked it out, we know we can do it. We've developed rocket technology to the point where this is not really that big of a problem. So, things can go either way. All right, so I just wanted to point that out. And it also prefaces another section here that I'll go through in a second. Let me check my time. Okay, I do have to hurry a little bit here because I need to get to something else. All right, so before we leave here, I want to point out something in the notes, which is solar energy. All right, you can calculate so here's the sun. You can calculate that the sun is emitting electromagnetic energy. Okay, that's what it does, light, primarily in the visible spectrum. And you can work out through a variety of means that power is 4 times 10 to the 26 watts. Now, we're here on Earth, Now this energy is going all around, and so if you calculate how much the Earth gets of that, all right, that is 7.3 times 10 to the 17 watts. Because the rest, you know, doesn't hit us, or it goes out in all directions. Now, this number, okay, is a number you might see when people talk about solar energy and stuff like that. The amount of solar energy or power from the sun actually hitting the Earth. And remember, a terawatt is 10 to the 12. So this is 7.3 times 10 to the 5th, or yeah, 730,000 terawatts. All right, so, you know, I mean, sometimes solar proponents, and I'm a solar proponent, will use that number and say, wow. And the thing is that, well, yeah, of course, but then the question is, can we utilize all that? And of course we can't, but we can utilize a lot of it. Now, finally, what I want to do is that if you take this and you divide it, so remember, this is WP, all right, works out to, remember, P is power per unit area. This is the Earth. It works out to 1,400 watts per meter squared, okay? And all you're doing there is you're taking this number and you're dividing by the area of an imaginary sphere at the Earth's location relative to the sun. So you're taking that total power divided by the area. All right, and now that is the power density above us. Now, on a very clear day, I know I'm getting busy here with my writing. On a very clear day, 1,000 watts per meter squared reaches Earth. Okay? And that is an important and convenient number to remember for solar power. And it basically means that on a very, very clear day, 400 of that out above us in space gets absorbed in the atmosphere. And so the best you can ever achieve, this is called full sunlight, is 1,000. All right, I got to move along because I got to get you ready for the homework too. Now, I'll just go through this real quick. I'll just go through it in words because I don't want to make this video too overly long. In the notes, you'll go through. Remember, we just discussed how there's all this methane on Titan. But what I've told you is this stored chemical energy on Earth, which includes methane, came from organic processes. It came from photosynthesis. So you might be asking yourself, well, where did the methane come from on Titan? Okay, because we aren't aware of life on Titan. And the answer is very simple. Just like stellar events can produce stored nuclear energy, stellar events can produce stored chemical energy just as easily. Now, what that has led to is sort of a very, very small fraction of scientists wanting to explore the possibility that this stored chemical energy, oil and such, is not really from photosynthesis, but really somehow from the stellar events that preceded our formation of the Earth, and so it got stored somehow. Now, the only thing I do, I mean, that is a possibility that has been mostly discounted, but I can't say that it is 100% discounted. It's like 99.9% discounted. And all I do in the notes is what I point out is that if you consider the fact that before there were plants on our planet, the atmosphere of the Earth was primarily carbon dioxide. And then over eons, plants have converted that carbon dioxide through photosynthesis into stored hydrocarbons, the carbon, including oil and coal and such. And if you work out the numbers, you work out that, because you can calculate basically the weight of that stored carbon in the early atmosphere, knowing a few things. And if you go through the calculation, you will find that the amount of stored chemical energy, stored oil, stored coal, is very consistent with that original weight of carbon in the primordial atmosphere before planets. And so I just included that because I don't want you to think that there's any mystery there about where that stored carbon came from, in the sense that the argument that it came from photosynthesis is well supported by considering that photosynthesis converted the amount of CO2 in the Earth's atmosphere a billion years ago, over that billion years, into organic matter. All right, so let's talk about chemical energy. And let me do it this way. So, stored chemical energy. All right, and I'm sort of going to jump through a few things here, and sort of jump to the point, because in the homework you're asked to calculate stored chemical energy, and particularly petroleum, and natural gas are alkanes. And alkanes are CnHn plus 2. So basically, like if N is 5, right? It's like the world's, it's the simplest thing in chemistry. You just put an H on either side. And then at the end. And if you remember your octet rule, and I go through this in the notes, I'm not going to go through it in detail here, but you will see that since hydrogen has 1 valence electron and carbon has 4, each of these carbon atoms has 8 valence electrons around it. Remember the rule of 8, and you need that you need that to figure out the bonds. All right, in the problem. So I don't want to give away the problem too much, but basically, all right, and natural gas is primarily methane, which is CH4, and so CH4 is just N equals 1. Okay, so you get it, and what has happened basically is that for petroleum and natural gas, and we'll discuss coal later, but for petroleum and natural gas, what has happened is that that those plants, that photosynthesis and such, okay, basically the plant wanted to make glucose and stuff like that for itself, but then when all those plants got compressed and everything over eons in the earth at high temperatures and pressures, basically all that organic matter, got formed into basically alkanes here, and that's the result. So all the petroleum, I keep misspelling. There's a funny thing about teaching at the blackboard, which is that for some reason being close to the blackboard makes you make mistakes, and I apologize if I make mistakes ever, but things like that, and for some reason the dimensions. But anyway, so this releases energy through burning this. So CnH2n plus 2. All right, so what is the reaction? Well, oxygen. So you burn something, including alkanes, by reacting with oxygen, and the products are CO2 and H2O. All right, and I haven't balanced the equation. I'm assuming people have had enough chemistry that they can at least follow the notes and perform things like balancing and stuff. But basically, what it comes down to is when you perform this reaction, you release energy, and that energy is equal to the bonds on the right, the product, I'll write it this way, the product bonds bond energies minus the reactant bond energy. So you have to calculate the bond energies, and you'll see that you know, I give you a table, and okay, so like here, I've already told you what the bonds are. The bonds are CH, so there's a certain number of CH here, and a certain number of CC. See, there's CH bonds and there's CC bonds, okay? And now, for those of you that have taken chemistry, all right, you can do the problem in homework too, using moles and bond energies per moles in terms of kilojoules per moles. All right, okay, that's fine. Okay, if you haven't taken a lot of chemistry and you don't know what a mole is, all right, basically I give you a table of these bond energies in electron volts, because of course each bond has a very tiny amount of energy, and so you can take all the bonds on this side, calculate all their energies, and subtract the bonds on this side, and as a parameter in the problem, in electron volts. All right, so you can do that. And so now, but what I want is I want then the energy per mass of the alkane molecule. So how do you look up that? Well, okay, so carbon weighs 12 atomic mass units. And so, you know, you do all that. See, the whole mole thing and the kilojoule per bond and moles take into account atomic mass units and things like that. But however you do it, you take the result of this calculation and you divide it by the mass. And I want it in BTU per kilogram, which sounds really odd because it's an English unit and an MKS, but there's a specific reason why I want you to give me the answer in BTU per kilogram for different values of N, and it'll be listed in the homework. So part of the job is you have to figure out the bonds, and I do it for O2. So let me just walk through quickly Chemistry 101 in terms of calculating molecular bonds, or figuring out what molecular bonds are. Okay, you did it in the notes for O2. So oxygen, if you go to the periodic table that I nicely supplied, you will see that oxygen is in the group 6 column. All right. Meaning it has 6 valence electrons. So O2, and I won't draw the bond yet, has 12 valence electrons. And the whole thing here is that you want to distribute those 12 valence electrons around the oxygen atoms so that each one has 8 around it, the octet rule. So you start with, okay, a single bond, which is, okay, a single bond is 2 valence electrons. So you try that first, a single bond. This is, you know, represented that way in the table. And so you took 2 and you have 12 total, and so then you put 10 around, and it's even. And so you would put 5 on either side, okay, to use up the other 10. And you would look at that and you go, that's not right, because each oxygen has 1, 2, 3, 4, 5, 6, 7. Okay, it doesn't like that. It's very unhappy. Okay, so what you do is you go up one more. You try a double bond, and that's schematically drawn this way. And now you took up 4. 12 minus 4 is 8, and so you put however you need to do it. You put 4 on either side here, because now there's a total of 12, and now it's happy because each one has 1, 2, 3, 4, 5, 6, 7, 8, and so this is O2. Oxygen forms by having a double bond with the other oxygen. So you have to do it for CO2. Okay, so you have C. So you do the same exercise for CO2, and that's part of the problem. And you know, honestly, you could look it up, but I mean, try it. I mean, because it's not hard. I mean, carbon is group 4, so there's 4 and 6 and 6, so there's a total of 16. And naturally, it's kind of, I mean, it's easy to think about it. There's going to end up being symmetric, and so you start trying, you know, different configurations, and to come up with the value. Whether these are double or single bonds, basically. So that's part of the exercise. And that's it for today. So basically, I'm going to post a solution to homework 1 right now, as soon as I upload the video. And I'm going to post homework 2, which homework 2 has a couple of fun problems. And then this problem of calculating the BTU per kilogram as a function of N for alkanes. All right, that's it for today. So we'll meet in the chat class on Tuesday.